Somewhere on a leopard, there's a pattern. Somewhere on a zebra, there's a code. Nobody designed it. Nobody drew it. No blueprint exists anywhere in nature that says, put the spots here, the stripes there. And yet every time, without fail, the pattern shows up. A formless clump of cells, dividing in the dark, somehow knows how to become a face, a wing, a stripe. For all of human history, that felt like magic. One man looked at it and saw math. Not metaphorically, literally. Equations hiding inside biology nobody had thought to look for. He wasn't a biologist. He was the man who had already invented the theoretical computer and cracked the Nazis' most secure code and asked the question that still defines artificial intelligence today. And in the last 2 years of his life, hunted by the same country he'd just saved, he turned to one final quiet mystery. Not machines, not war, not code, just a question a child could ask, and almost no adult could answer. Why does a zebra get stripes and a leopard get spots? His name was Alan Turing, and this was the theory nobody expected, the one he never lived to see the world catch up to. This is not another biography. This is the science behind the genius, and the darkness behind the science.
Welcome to Dark Science Mind.
By 1950, Alan Turing had already done enough for 3 lifetimes. He'd built, on paper, the theoretical machine underneath every computer that would ever exist. A machine so simple in concept and so vast in consequence that it still forms the basis of every phone, laptop, and server on the planet. He'd helped break Enigma and helped end a war years earlier than it might otherwise have ended. He'd asked whether a machine could think and given the world a test for it that we still argue about today, in an age of artificial intelligence he never lived to see. Most people at that point coast. They defend the legacy. They give lectures. They let the world catch up. Turing didn't know how to do that. He was working at Manchester University by 1948, surrounded by one of the first working stored program computers on Earth, a machine nicknamed Baby, writing some of the first real software in human history. But a working computer, to Turing, wasn't a finish line. It was a tool. And by the early 1950s, he'd pointed that tool somewhere almost nobody expected. Away from cryptography, away from artificial intelligence, away from the war that had defined the previous decade of his life, toward biology, toward a question so basic that most trained scientists had simply stopped thinking of it as an open question at all. How does a living thing know what shape to become? The oldest question nobody had answered. To understand why this mattered, you have to understand how deep the mystery actually goes. A human being begins as a single fertilized cell. That cell divides into 2 identical cells. Those 2 divide into 4, then 8, then 16. For a while, those cells are essentially interchangeable. Same DNA, same starting chemistry, no visible differences between them. And yet, a few weeks later, some of those cells have become the beginnings of a spinal cord. Others have become the beginnings of a heart. Others will become skin, or eyes, or fingers, spaced out with startling, repeatable precision. Nothing physically moves the cells into place. There's no tiny architect inside the embryo directing traffic. Somehow, the pattern simply emerges, the same way it emerges on a butterfly's wing or a seashell's spiral. or the ridges on the roof of your own mouth. By the early 1950s, biologists had spent nearly a century documenting what happens during development. Entire careers were built cataloging which cells became what and when. But almost nobody could explain the deeper mechanical question underneath it. What actual physical or chemical process forces a uniform ball of identical cells to break its own symmetry and organize itself into something as staggeringly complex as a living body? It was, in a real sense, one of the last great unsolved problems in biology. And Turing, who had no formal training in biology at all, became convinced the answer wasn't going to be found by looking harder at cells. He thought it was going to be found in chemistry and in mathematics, the same intellectual toolkit he'd already used to dismantle a Nazi cipher and define the theoretical limits of computation. Why a codebreaker went looking in biology. It's worth pausing here, because this wasn't a random hobby. Turing had spent the 1930s asking what a calculation fundamentally was, underneath all the notation mathematicians used to describe it. He'd spent the war years asking what a secret fundamentally was, underneath all the scrambling the Enigma machine used to hide it. By 1950, with the Turing test, he was publicly asking what thinking fundamentally was, underneath all the behavior we associate with an intelligent mind. Morphogenesis was the same question aimed at biology. What does shape fundamentally consist of underneath all the visible complexity of a living organism? In every one of these cases, Turing's instinct was identical. Assume the complexity on the surface is not the real story. Assume there's a simpler, hidden mechanism generating it. Go find the mechanism. It's the same mind walking into 4 completely different rooms and asking the same question every time. The paper. In August 1952, the Royal Society published Turing's paper, The Chemical Basis of Morphogenesis. It's a strange, quietly radical document, dense with equations, but built around an idea simple enough to sketch on a napkin. Turing proposed that pattern in living tissue could emerge from the interaction of just 2 chemical substances, which he called morphogens, form-generating substances spreading through developing tissue. He imagined 2 of these morphogens working against each other. The first, an activator. Wherever it's present in sufficient concentration, it switches something on. Pigment production, cell specialization, structural growth, whatever the biological context calls for. The second, an inhibitor. It does the opposite. It suppresses that activity and prevents it from spreading unchecked. On their own, spreading evenly and at the same rate, these 2 chemicals would simply blend into a flat, uniform, boring soup. No pattern, no structure. Nothing interesting happens, mathematically or biologically. But Turing found something almost nobody expected buried inside the equations. If the inhibitor diffuses through the tissue faster than the activator, even slightly faster, the system doesn't settle into uniformity. It becomes unstable. And out of that instability, structure spontaneously appears. The math, in plain terms. Here's the mechanism without the equations. Picture a small region where the activator happens to be very slightly more concentrated than its surroundings, just by chance, just by the natural randomness of chemistry. That small peak reinforces itself. The activator, true to its name, boosts its own production locally. The peak grows. But as it grows, it also triggers production of the inhibitor. And because the inhibitor spreads faster, it races outward from that peak, forming a kind of chemical wall, suppressing activator production in a ring around the original peak, without erasing the peak itself. Now picture that happening not once, but simultaneously, at many points across the surface of a developing embryo. Each peak creates its own zone of suppression around it. Each zone of suppression prevents new peaks from forming too close by. But it can't stop new peaks from forming just outside that zone. Repeat that interaction across a whole surface, thousands of times over, and you don't get randomness. You get rhythm. Evenly spaced spots, regularly repeating stripes. A structure that looks, to the naked eye, like it must have been carefully designed, and was actually just the natural mathematical consequence of two chemicals moving at two different speeds, competing for the same space. Turing called this a reaction-diffusion system, and the deeper implication was almost philosophical. Pattern doesn't require a blueprint. It doesn't require a plan or a designer or step-by-step instructions written into every cell. It can emerge automatically and predictably out of nothing more than simple local rules interacting at scale. No architect, just chemistry, obeying math at every point on a growing surface, all at once. What the theory actually predicted. Turing didn't stop at the abstract principle. He used it to make specific, testable predictions. He argued that depending on the relative speeds and strengths of the activator and inhibitor, and depending on the shape and size of the surface they're spreading across, this same underlying mechanism could produce wildly different results. Spots on one animal, stripes on another, blotches, whorls, spirals. He even predicted something that seemed strange at the time, that the same reaction-diffusion system on a long, tapering surface like a tail might naturally shift from spots near the wide end to stripes near the narrow end, simply because the geometry of the surface changes how the chemicals interact. Decades later, that specific prediction would be confirmed almost exactly in the tails of real animals. He also predicted that this mechanism wasn't limited to skin pigment. In principle, the same activator-inhibitor logic could explain the spacing of fingers and toes, the branching pattern of blood vessels, the ridged pattern on the roof of a mammal's mouth, and the placement of hair follicles or feathers. At the time, this was essentially unprovable. Nobody in 1952 had the tools to watch chemical concentrations move in real time through living embryonic tissue. Turing was proposing a mechanism nobody alive could actually see. A computer used on life itself. Here's a detail most retellings of Turing's life skip entirely. He wasn't just theorizing about morphogenesis with pen and paper. He was one of the first scientists in history to use an electronic computer to simulate a biological process. At Manchester, using the same machine he'd helped bring into working order years earlier, Turing ran numerical simulations of his reaction-diffusion equations, effectively asking the computer to grow patterns according to his rules, and then checking whether the output resembled anything found in nature. Machine and biology feeding directly into each other in a way that wouldn't become a standard scientific practice for decades. It's a strange, quiet historical footnote. The same man who once used a machine to defeat an enemy's secret code was now using a machine to try to read the secret code hidden inside a living body. He had follow-up work planned. Correspondence from the period shows he intended to extend the model into more complex, three-dimensional patterns. not just simple repeating structures on a flat or cylindrical surface, but the far messier geometry of an actual developing organism. He never got the chance to finish it. The year everything collapsed. The same year his morphogenesis paper was published, 1952, Turing's personal life collided catastrophically with the laws of the country he'd helped save. In January of that year, his house was burgled. He suspected the burglar was connected to a man he'd been seeing, Arnold Murray. Turing went to the police to report the crime. In the process, with the same plain, unguarded honesty he brought to every mathematical proof, he told the police about his relationship with Murray. He wasn't caught in a lie. He simply told the truth, the way he told the truth about everything, assuming, perhaps, that the truth deserved to be treated fairly. It wasn't. Both men were charged with gross indecency, under a law that had already ruined countless lives in Britain. Turing didn't deny the charge and didn't perform remorse for the court. He described what had happened plainly, the way he might describe the steps of an equation. He was given a choice: prison or a course of hormonal treatment, chemical castration using synthetic estrogen intended to eliminate his libido. He chose the injections, in large part, by his own account, because prison would have meant losing access to his work. And work, for Turing, was never a side interest. It was closer to the center of who he was. For a year, while quietly continuing to publish and think about the mathematics of pattern formation, Turing's own body was being chemically reshaped by the state. The hormones caused impotence. They caused his body to develop breast tissue. He tried, in letters from this period, to keep his familiar, dry, ironic sense of humor about what was happening to him. But the isolation deepened. His security clearance was revoked. A mathematician who had once been trusted with his country's deepest secrets was now treated as a security risk, simply because of who he loved, at the height of Cold War paranoia about blackmail. The last working week. Friends who saw Turing in his final 2 years described someone who kept working, kept publishing, and, remarkably, kept some of his sense of humor intact. But they also describe a growing weariness, a man who had started seeing a psychiatrist, a man who mentioned, more than once, how strange it felt to be constantly, quietly watched. On June 8, 1954, Turing was found dead in his home by his cleaner. Cyanide poisoning. A half-eaten apple on the nightstand. The inquest ruled it suicide. No note was ever found. His mother never accepted that verdict. She spent the rest of her life insisting his death was accidental, the result of careless handling of chemicals he kept at home for casual experiments, a habit he'd had since childhood. There's real ambiguity here that historians still debate. His hormone treatment had ended a full year before his death, and, in one of the more haunting details of his final days, he had left a list of tasks for the following week when he was due back at the lab. Not, on the surface, the last act of a man who had already decided not to return. We don't get a clean answer, and given how the rest of his life went, one secret he wasn't allowed to tell, and one secret the state punished him for telling, maybe it fits, in its own bleak way, that even his death resists a tidy explanation. He was 41 years old. Among the smaller, quieter questions he left unanswered, sitting right next to the far larger ones about minds and machines, was this one. How much further would the stripes have gone if he'd had the time to keep chasing them? The proof that came too late. For decades after his death, Turing's morphogenesis paper was treated as a curiosity, a brilliant man's side project, a minor footnote sitting next to the computer, the code breaking, and the test that carries his name. Biologists respected it. Almost nobody could test it. The tools to actually observe chemical concentrations moving in real time through living embryonic tissue simply didn't exist yet. That started to change in the 1990s and 2000s, as genetic sequencing, molecular biology, and real-time imaging finally caught up to the theory. Researchers began finding actual physical evidence of activator-inhibitor chemical pairs, behaving almost exactly the way Turing's equations predicted more than 50 years earlier. In the regular ridges on the roof of a mouse's mouth, in the precise spacing of hair follicles across skin, in the formation of digits, fingers and toes during limb development, where a Turing-style reaction-diffusion mechanism, working alongside other genetic signals, appears to help determine how many digits form and how they're spaced. In the specific shift from spots to stripes along the tapering tail of certain fish and mammals, the exact geometric prediction Turing had made, using only equations and a room-sized computer, decades before anyone could check it. The theory a dying, isolated, hunted man had sketched out in his last working years turned out to be substantially, remarkably correct. He never saw any of that confirmation. He didn't live long enough to know whether the equations he'd built, in the shadow of a criminal trial and a chemical punishment, were actually right. Alan Turing built the theoretical foundation for the machine that now powers almost every aspect of modern life. He helped save a nation using a machine built specifically to keep secrets. He asked whether a machine could ever truly think, a question we still haven't fully answered, even now, in an age of artificial intelligence he could only have imagined. And in the very last theory he ever published, while being punished by his own government for who he loved, he found the hidden mathematics sitting quietly inside a stripe on a zebra, a spot on a leopard, the ridges on the roof of a mouse's mouth. Proof that even the wildest, most organic-looking patterns in nature aren't random. They follow rules. Simple rules, repeating at scale, with no architect required. The tragedy sitting underneath all of it is almost too neat to be comfortable. The man who finally found the rule for how nature builds a body was never, in his own country, in his own lifetime, allowed to simply be the person his own body and mind had made him.